Okay. Yeah, so I was a bit scared when Rob said that Kubernetes makes everything harder, and maybe it turns out I'm working a lot on things that just make everything harder. So I'm afraid I'll talk about differentiable programming. Um, okay, how does this work? Does this work? Oh, it doesn't work? How do I? Yeah. So, I mean, we all know there's been an incredible progress in machine learning. So you see kind of chatbots, kind of reasoning about jokes and so on. And so I think I won't go into that. But I mean, you might think, okay, are we approaching like artificial general intelligence? But then our instincts tells us that, replacing everything with the big black box is insufficient for the stuff that we need to do. We want to do uncertainty quantification and so on. And so there's a lot of interest in physics-informed machine learning approaches. And the question is, of course, okay, where do you put the physics, right? So in a machine learning model, we have the model, we have the loss, and we have the label. And so ideally, we want to inject the physics into each of these, different components of a machine learning model. And a kind of funny coincidence is that gradients are a key mechanism to inject domain knowledge into each of these little boxes. So it's not only about the model, but it's also about the loss and the labels. And this kind of importance of gradients kind of leads us to differentiable programming. And so if you think about what the core of machine learning is, it's really not about like the architecture, because there are many architectures, but it's kind of searching through like a very extremely high dimensional space of algorithms. And so in these high dimensions, trillion dimensions, gradients are very crucial because you can't do numerical differentiation in these things. And so that requires both differentiable models and differentiable losses. And so then you have like some space of algorithms and you just move through that space and try to find like your target function. Okay, let's talk about the model. How do we inject physics there? So the classic kind of orthodox approach is, okay, we have like one brain, and so we have one model and it will basically do everything for us. And we just throw data at it and it will learn it. And so with sufficient data, this can work, but increasingly, people think a lot about architectures, because architectures are a way to add structure to the space of programs that you're looking through. And so instead of looking through like a huge space of programs by restricting the class of algorithms, you're searching through smaller, kind of more relevant space. And so that becomes much more interpretable and also much more data efficient. So there are things like QCD-aware neural networks, Lorentz-invariant neural networks, Hamiltonian neural networks. And this starts to look much more like programming and not like a single like brain that you just train. And so you are much more data efficient. You might get, train a big neural network, but you would need much, much more data. And so this is this inductive bias that Sean mentioned. And so how do you do this? This is kind of this approach where, we start with a neural network and then we add structure, right? So we start with something that is differentiable, like a feed-forward neural network, and we add components like attention mechanisms, embeddings, and whatever recurrent structures. And so we start from the neural network and we're modifying it and add structure. But you can also go the other way around, where you say, okay, we already have a lot of physics structure in our code that already encodes our physics intuition. With reconstruction, we have a certain order, we first do tracking, calorimetry, and so on. And this is all domain knowledge that is that we put into our code. And so we could also just start from the code and make it differentiable instead of starting from something differentiable and adding structure. And so this is kind of this main point of view from differentiable programming. So instead of having like one big block, black box of kind of machine learning code, you have like individual things, and then there might be kind of more machine learning parts of that, and there might be some things that are not machine learnable. For example, you have maybe like machine learning based track candidate identification, and then the track fitting itself is not machine learning because it uses like a Kalman filter and so on, or maybe it's machine learning but not deep learning. But the view of differentiable programming is that, okay, maybe you can still view it as a kind of end-to-end neural network that you can differentiate through it, and you can jointly optimize all of these things. And so you just pick and choose, you pick your battle. So where are the things that are, where's the structure that is important to add, and where are the things that you can let loose, and you just let the machine learning fill in the blanks. And so currently, how we do it, of course, we already enforce the physics somehow. And the way that we do like per task training. So instead of doing like this end-to-end optimization, we like rip out the individual machine learning components, we train them separately, and then we inject it back into the pipeline, and then we run, let's say, reconstruction or analysis. But it's not clear that this is the optimal, because there's no way that for example, like downstream analysis can affect the tracking, right? We train the tracking on whatever tracking training data we have, and doesn't know anything about the downstream analysis use cases unless we put it in kind of in the way that we prepare the training data. And so with differentiable programming, by just making this entire thing differentiable, instead of ripping them out and putting them back in, you can have like an end-to-end differentiable pipeline that you then jointly train. And so whatever downstream feedback mechanisms you have can travel all the way back to the kind of more upstream parts of the pipeline. And in some sense, this can affect. This is like an additional feedback mechanism that's useful. So the question that is, I think, absolutely unclear right now is how big the gain is versus this per task training. Maybe we're already pretty good, and it doesn't add much. And another important question is, okay, how big can we make these machine learning blocks, and how much structure is really necessary? So you see things like the single shot particle flow on thousands of particles that is just like more or less particle flow elements in, and then reconstruct the particles out. And so we're seeing, I think, like a trend where the machine learning blocks can become much bigger than maybe we thought like a couple of years ago. So this was the model, then the labels. So I think the best example of differentiable programming to improve the labels is this simulation-based inference. And so the idea is, normally what we would do is we would train the machine learning model to, let's say, predict what the class of the event is. So is it like a signal or background? And so that would be kind of the input of the simulator. So either you run the simulator as a signal simulator, or you run the simulator as a background simulator, and that's the label that you would use. But increasingly, there's like a interest in, okay, while we're running the simulator, can we extract better labels in order to improve the training? And the answer is yes, and particularly if you're able to extract gradients from the simulator, then those labels become much more powerful. And so it's basically this this extension for, you start with binary classification, you can turn it into a regression problem, which makes it much easier. So here you have like this tug of war between the dots at the bottom and the top, and so they try to pull at the function, and you find some kind of equilibrium. If you turn it into a regression problem, it's much easier, because you have kind of labels that are much closer to the function. And if you want to if you have additional gradient information, you can learn kind of the function much more easily. It's kind of intuitive. If you have a function, you have more information about the function, it's much easier to learn the function. And if you not only have the function value, but also the gradient, it just adds information, and it's clear that this helps. And so for this, you need like a differentiable simulator. We heard a lot about differentiable simulators, and so in this case, you need differentiable matrix elements, and so that's something that's happening. And this is pretty far away from machine learning, but it's using differentiable programming for improving the labels. So I talked about this. Yeah, so then the last thing is, okay, can we improve the losses through differentiable programming? And so there are like kind of these type of patterns where, you might want to do differentiable analysis optimization, where you have like an analysis configuration, let's say neural network weights, and then normally instead of evaluating against a standard loss, like binary cross entropy and so on, and then sticking it back into the analysis pipeline, and then evaluating all systematics and so on, you can just kind of directly run the downstream analysis and see the physics performance, and you can backpropagate. If you have the if the statistical analysis, for example, is differentiable, you can backpropagate through the analysis configuration, optimize it directly, instead of kind of just hoping for the best that it's working. And so a very similar idea is differentiable design optimization, where you have maybe like a detector configuration, and you want to see, okay, is that a good detector design? And if you have a differentiable simulation and a differentiable analysis, you can just look at the physics performance and optimize the detector design. So this is a very ambitious idea. So here, this is NEOS. So here we see that this can definitely find other solutions than what you would find with standard machine learning techniques, and it can kind of incorporate systematic uncertainties. But I did want to show this. So unfortunately, this doesn't show on the PDF. So there's a animation related to this. But the idea is here. Okay, let's say you want to design a surface such that if there's like a stream of water coming out of this pipe, the stream of water lands on this line. Okay, what should the surface be? And amazingly, so on the left-hand side, you see a randomly initialized surface, and you can imagine, okay, the water is splashing left and right. But by basically having this in an end-to-end differentiable way, you can just optimize the surface directly. And so this is optimizing hardware, through a differentiable downstream physics simulation. And so this amazingly works. And the first time I heard about the differentiable design optimization for hardware, I thought, okay, this is crazy. And so this is kind of encouraging that for simple things, we see it works. And so it's kind of interesting to see how far we can take it. So there are some initial things in high energy physics to try this out. And so we'll have a talk about differentiable design optimization in our parallel. And so this is my end. So there's like also automatic differentiation for a lot of other things. So even if you're not thinking about like this grandiose end-to-end optimization vision, we use gradients, a lot of things like error propagation and tracking and so on, or just fitting, maximum likelihood fitting, and gradients are very useful in these respects, and automatic differentiation is just a very efficient tool to compute gradients. And so there's a lot of use cases kind of beyond machine learning where this is useful, and it's kind of like the most under advertised kind of technology in the last 40 years. I mean, automatic differentiation was invented in the 70s and 80s. And so it's kind of funny that we're just talking about it now. So yeah, so this is my summary. So okay, gradient information is useful for all kinds of machine learning things. We can improve the model by adding inductive bias. We can improve the labels, like with simulation-based inference. We can improve the loss, so we can have downstream assessment of the result of the machine learning model, that guides the model in a useful way. And so that's not a new idea. So Jürgen Schmidt, who was one of the kind of pioneers of machine learning, talked about making the world differentiable 30 years ago. And so now it's interesting that we're starting to talk about this in high energy physics. Okay, so there's a much longer talk for this, but okay, I'm already 5 minutes over.